May 3, 1942. Federal Shipbuilding and Dry Dock Company, Kearney, New Jersey. The champagne bottle struck the bow at exactly 10:15 in the morning, but what mattered more was what had happened in the 7 months prior. The destroyer sliding down the ways into Newark Bay carried a hull number that would become legendary, DD-445, USS Fletcher, the first of her class. Preparing and narrating this type of story took us long efforts and hard work. So, if you are enjoying the story, please consider subscribing to our channel. What neither the assembled dignitaries nor the Navy brass watching from the reviewing stand fully understood was that this ship represented something far more revolutionary than her 5-inch guns or torpedo tubes. Fletcher embodied a transformation in how warships could be built, a transformation rooted not in naval architecture, but in an industrial insight borrowed from an entirely different field. The ship's all-welded hull, constructed from pre-fabricated sections assembled like components in a bridge, would enable production speeds that traditional maritime wisdom considered physically impossible. Within 18 months, destroyers of this class would be launching every 17 days from a single shipyard. The methods that made this possible would challenge everything the Navy had believed about how fighting ships must be constructed. The mathematics were brutal and undeniable. In December 1941, the Japanese attack on Pearl Harbor had crippled American Pacific naval power. Replacing destroyed vessels through traditional construction methods would require years. The Navy needed destroyers immediately, needed them in overwhelming numbers, and needed construction approaches that could scale beyond anything attempted in naval history. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Traditional destroyer construction in 1941 followed practices unchanged since the First World War. Naval shipyards built destroyers through craft methods requiring specialized workers and months of careful assembly. Each vessel was effectively unique, custom-fitted throughout construction. Destroyer hulls were riveted together plate by plate, each rivet heated, inserted, and hammered by skilled riveters working in teams. A single destroyer required approximately 500,000 rivets. The process was methodical, time-consuming, and fundamentally resistant to rapid scaling. Bath Iron Works in Maine, one of America's premier destroyer builders, could produce perhaps one destroyer every 40 to 50 days under ideal conditions. Most naval yards worked considerably slower. The Navy's pre-war destroyer force had been built over decades, not months. Federal Shipbuilding and Dry Dock Company entered this landscape as an outsider with radical ideas about how ships should be constructed. Founded in 1917 by United States Steel Corporation to build merchant vessels for World War I, Federal had survived the difficult interwar years by building commercial ships when military contracts disappeared. But Federal's true advantage lay hidden in its corporate ancestry. The company had been established not by traditional shipbuilders, but by bridge engineers from American Bridge Company, U.S. Steel's structural engineering subsidiary. This lineage would prove decisive. In 1915, American Bridge had fabricated hull sections for seagoing tankers using bridge construction methods rather than traditional shipbuilding techniques. Instead of cutting and fitting steel plates individually at the vessel site, bridge engineers prefabricated large hull sections in workshops, then transported completed assemblies to shipways for final joining. The approach had worked remarkably well for commercial vessels. It remained largely forgotten by 19 bases, 41, dismissed by traditional naval architects as unsuitable for warships requiring structural integrity under combat stress. Federal's management, however, remembered these methods. They recognized that techniques proven in bridge construction could revolutionize destroyer production if applied systematically. The challenge began with a fundamental problem facing all American destroyer construction in early 1941. The Navy needed to rapidly expand the destroyer fleet to counter both German U-boats in the Atlantic and Japanese naval forces in the Pacific. Existing destroyer classes, built under treaty limitations that restricted tonnage, proved inadequate for the long-range Pacific operations the Navy anticipated. The new Fletcher-class design, finalized in 1939 and 1940, represented the first American destroyers designed without treaty restrictions. At 2,050 tons standard displacement, Fletchers were significantly larger than their predecessors. They mounted 5 5-inch dual-purpose guns, 10 21-inch torpedoes in 2 quintuple mounts, and carried sophisticated anti-submarine detection equipment. The design was sound. The question was whether American industry could build enough of them fast enough to matter. Traditional naval construction approaches offered no pathway to producing the hundreds of destroyers the Navy would need. Bath Iron Works, despite its excellence, could build perhaps 12 destroyers per year at maximum capacity. Federal Shipbuilding recognized this limitation and proposed something unprecedented. In October 1941, as Federal prepared to lay the keel for USS Fletcher, the company's engineering leadership made decisions that would transform destroyer construction. They would build Fletcher using all-welded construction instead of riveting. They would prefabricate major hull sections in workshops away from the building way. They would treat destroyer construction as a systematic assembly process rather than a craft tradition. Each decision violated conventional naval wisdom. The Navy's Bureau of Ships viewed riveted construction as proven and reliable. Rivets allowed flexibility as hull plates shifted under stress. Welding created rigid connections that might crack under combat loading. Prefabrication seemed impossible for the complex curved sections of destroyer hulls, and systematic assembly contradicted generations of shipbuilding practice. Federal's chief engineer made his case with brutal simplicity. Welding was faster than riveting by an order of magnitude. A welded seam could be completed in hours versus days for equivalent riveted connections. Prefabrication allowed parallel production. While workers assembled one section on the building way, other crews could fabricate the next sections in workshops. Multiple teams working simultaneously would collapse construction timelines. The systematic assembly approach had proven successful in automotive production and aircraft manufacturing. There was no fundamental reason it couldn't work for destroyers if components were designed for assembly rather than custom fitting. The Bureau of Ships remained skeptical but approved Fletcher's construction using Federal's proposed methods. The approval came with strict conditions. Federal would demonstrate that welded destroyer hulls could pass structural tests. They would prove that prefabricated sections could be joined with sufficient structural integrity, and they would meet the same strength and seaworthiness standards as traditionally constructed destroyers. Federal's engineers began by completely reimagining how a destroyer hull could be divided for prefabrication. Traditional construction built destroyers longitudinally, assembling the keel and working upward plate by plate from bow to stern. Federal's approach divided the hull into major transverse sections: the forward section from bow to the forward fire room, the midships section containing engine spaces, the aft section from the aft fire room to the stern. Each major section was further divided into sub-assemblies that could be fabricated in workshops. Bulkheads, deck sections, hull plating, and structural frames were all prefabricated to precise dimensions. The key innovation was tolerance control. Traditional shipbuilding accepted wide tolerances, with skilled craftsmen custom-fitting components during assembly. Federal applied bridge engineering standards, manufacturing components to tight tolerances that allowed them to fit together without adjustment. This precision manufacturing required completely different quality control approaches. Every fabricated component was measured and inspected before leaving the workshop. Dimensions had to match engineering drawings within fractions of an inch. Any component that failed inspection was reworked or scrapped rather than custom-fitted during assembly. The welding challenge proved more complex. In 1941, electric arc welding for shipbuilding was relatively new technology. Most welders learned their craft on thinner materials. Destroyer hull plating ranged from 3/8 inch to 3/4 inch special treatment steel, significantly thicker than commercial vessel plating. Welding thick steel plates required controlling heat input to prevent warping while ensuring full penetration for structural strength. Federal's welding engineers developed specific procedures for destroyer construction. They specified preheat temperatures to reduce thermal stress. They designed weld joint geometries that allowed inspection. They established welding sequences that minimized distortion. Most critically, they trained welders systematically. Rather than requiring years of apprenticeship, Federal taught specific welding procedures for specific applications. A welder might learn only how to weld vertical bulkhead seams or horizontal deck plate joins. This specialization allowed rapid training while maintaining quality. By late 1941, Federal had transformed its Kearney facility to support the new construction approach. Large fabrication shops occupied buildings adjacent to the building ways. Overhead cranes capable of lifting 50-ton assemblies connected workshops to shipways. Rail lines allowed transport of major sections. The facility layout embodied the production philosophy. Steel arrived at one end, was cut and formed in fabrication shops, assembled into major sections, then transported to building ways for final joining. The entire process flowed in one direction with minimal backtracking or rework. USS Fletcher's keel was laid on October 2, 1941. What happened over the next 7 months would validate or destroy Federal's revolutionary approach. The construction proceeded in phases that revealed the power of systematic prefabrication. The keel and lower hull plating went down first, welded together on the building way. While this foundation was being laid, fabrication shops were already building the forward bow section complete with anchor handling equipment, chain lockers, and crew berthing spaces. The midship section, containing boiler rooms and engine spaces, was being assembled with machinery foundations already installed. This parallel production created an entirely different rhythm than traditional sequential construction. By the time the keel was complete, major hull sections were ready for installation. Massive cranes lifted the prefabricated bow section, positioned it precisely, and welding crews joined it to the keel structure. What would have taken weeks of plate-by-plate riveting was completed in days of welding. The engineering spaces presented the greatest challenge and the most impressive demonstration of prefabrication's potential. Traditional destroyer construction installed boilers and engines after the hull was substantially complete, lowering machinery through deck openings into spaces that were already cramped and difficult to access. Federal's approach fabricated entire engineering sections with machinery already installed. Boilers were mounted on their foundations in workshops where access was unrestricted. Piping was installed and tested. Auxiliary equipment was positioned and secured. When the complete engineering section lifted onto the building way, it was a fully functional unit requiring only external connections. This approach demanded extraordinary precision. The engineering section had to mate perfectly with fore and aft hull sections. Pipe connections, electrical runs, and structural attachments all had to align. Any dimensional error would require extensive rework. Federal's tolerance control proved sufficient. The engineering section dropped into place and welding crews sealed the connections. By March 1942, USS Fletcher's hull was structurally complete. The superstructure, bridge, and deck houses were being installed using the same prefabrication approach. Each element had been built in workshops and lifted into position as complete assemblies. The ship's 5.5-inch gun mounts were installed on foundations that had been built into the prefabricated deck sections. Fire control equipment, radar antennas, and torpedo mounts all went in according to systematic installation sequences. Nothing was custom fitted. Every component had been designed to bolt or weld into place according to precise specifications. On May 3, 1942, just 7 months after keel laying, USS Fletcher slid into Newark Bay. The time from keel to launch, 212 days, was faster than any previous destroyer had been built in the United States. More impressive still was what the achievement represented. Federal had proven that destroyers could be built using industrial production methods. The Navy's acceptance trials would determine whether speed had compromised quality. Fletcher underwent extensive testing through May and June 1942. Hull strength tests measured structural integrity under stress loading. Speed trials confirmed the ship could exceed 37 knots. Weapons systems were tested and validated. On June 30, 1942, USS Fletcher was commissioned into the United States Navy. Every structural test had been passed. The all-welded hull proved stronger than riveted construction, not weaker. Prefabricated sections joined together showed no weakness. The ship met every performance specification. The validation was complete. Federal's revolutionary construction approaches worked. destroyers could be mass-produced using systematic industrial methods. The implications transformed American destroyer construction practically overnight. The Navy immediately authorized expansion of Fletcher-class production. 11 shipyards across the United States would build Fletchers using Federal's proven methods. Bath Iron Works in Maine, Seattle-Tacoma Shipbuilding in Washington, Boston Navy Yard in Massachusetts, Consolidated Steel in California, Gulf Shipbuilding in Alabama, and others all adopted all-welded construction and prefabrication techniques. Federal shipbuilding itself ramped up production dramatically. By fall of 1942, the Kearney Yard was building multiple destroyers simultaneously across several building ways. The fabrication shops ran 3 shifts daily, producing hull sections, superstructure elements, and equipment modules in continuous flow. The speed improvements proved extraordinary. Fletcher herself had required 212 days from keel to launch. By mid-1943, Federal was launching destroyers in 103 days, exactly half the time. The record holder, USS Melvin, went from keel laying to launch in 103 days, and from launch to commissioning in just 52 additional days. Bath Iron Works achieved even more impressive production consistency. Between 1942 and 1945, Bath produced 67 destroyers of the Fletcher class and its successors. Excluding first-of-class ships, which always required more time, Bath commissioned a new destroyer every 17.3 days on average, with standard deviation of just 2.5 days. The consistency was as remarkable as the speed. Traditional craft construction varied widely in completion times, because each ship faced unique challenges requiring custom solutions. Systematic industrial construction with prefabricated components removed most variables. Barring material shortages or equipment delays, production timelines became predictable and repeatable. The workforce transformation paralleled the production revolution. Federal shipbuilding employed approximately 5,000 workers in 1940. By 1943, employment exceeded 52,000. The vast majority of new workers had never built ships before. Many had never worked in heavy industry. Federal's training approach mirrored its construction philosophy. Rather than teaching comprehensive shipbuilding skills, training programs focused on specific operations. A worker might learn only how to weld bulkhead seams or install electrical conduit or fit pipe sections. This narrow specialization allowed training times measured in weeks rather than years. Women entered the workforce in significant numbers, particularly in welding trades. Pre-war assumptions that welding required male strength proved entirely wrong. What welding actually required was steady hands, good hand-eye coordination, and careful attention to procedure. Women demonstrated equal or superior capability in many welding applications. The democratization of skilled labor that Federal's approaches enabled carried implications far beyond wartime destroyer production. By proving that complex manufacturing could be performed by trained workers rather than requiring generational craft expertise, Federal validated industrial approaches that would reshape American manufacturing for decades. Preparing and narrating this type of story took us long efforts and hard work. So, if you are enjoying the story, please consider subscribing to our channel. The production statistics by mid-1943 told a story of transformation that maritime experts still struggled to comprehend. Federal shipbuilding at Kearney was producing destroyers faster than any yard in the world. On a single day in May 1942, Federal launched 4 destroyers in a 50-minute period. The spectacle drew journalists and naval officers who watched in disbelief as ships slid down adjacent ways in rapid succession. By July 1943, Federal claimed construction records that seemed impossible just 2 years earlier. USS Dashiell, a Fletcher-class destroyer, went from keel laying to commissioning in 170 days. USS Thorn, a Gleaves-class destroyer, achieved commissioning in 137 days total. These weren't experimental prototypes. These were fully combat-capable warships meeting every Navy specification. The speed came from relentless optimization of every construction phase. Federal's engineering teams analyzed production data continuously, identifying bottlenecks and implementing improvements. When welding crews waited for crane availability, Federal added more cranes. When fabrication shops couldn't keep pace with assembly demand, Federal expanded shop capacity and added shifts. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The systematic approach extended beyond the physical construction to supply chain management. A Fletcher-class destroyer contained approximately 15,000 individual components beyond the steel hull itself: engines, boilers, generators, pumps, electrical equipment, weapons systems, fire control directors, radar, sets, communications gear, anchors, chains, propellers, rudders, and thousands of smaller items all had to arrive at the shipyard precisely when needed. Federal established supplier relationships that resembled automotive industry practices more than traditional shipbuilding. Major equipment suppliers received contracts specifying delivery schedules months in advance. Components were designed for interchangeability across multiple ships. When USS Fletcher's boiler supplier delivered units, those same boilers could install in any Fletcher-class destroyer under construction. This standardization proved crucial for rapid scaling. As Fletcher-class production expanded to 11 yards, suppliers produced components that could ship to any facility. Bath Iron Works could install the same turbines as Federal Shipbuilding. Seattle-Tacoma used identical fire control systems. The destroyers were functionally identical regardless of which yard built them. The all-welded construction that had seemed so radical in 1941 became standard practice by 1943. Every Fletcher-class yard adopted welding because the productivity advantages were undeniable. A riveted destroyer hull required approximately 500,000 rivets. Each rivet needed heating, positioning, and hammering by a crew of 3 or 4 workers. A skilled riveting gang might install 100 rivets per shift. Welded construction eliminated riveting entirely. Electric arc welding joined plates with seams that were stronger than the surrounding metal. A single skilled welder could lay weld beads covering the same area that would require hundreds of rivets. The time savings exceeded 90% for hull fabrication. Structural benefits complemented the speed advantages. Riveted hulls had stress concentrations around every rivet hole. Under combat loading or heavy seas, rivets could shear, allowing plates to separate. Welded seams distributed stress continuously across the joint. Impact loading from nearby explosions was less likely to cause structural failure. The Navy's initial skepticism about welded construction disappeared as Fletcher-class destroyers entered service and demonstrated exceptional durability. Ships survived damage that would have sunk riveted vessels. USS Fletcher herself would serve through some of the Pacific War's most intense surface actions and emerge structurally sound. The combat debut came quickly. USS Fletcher arrived at Noumea, New Caledonia on October 5, 1942, just 3 months after commissioning. The ship immediately entered the Guadalcanal campaign, the desperate struggle for control of the Solomon Islands that would determine the Pacific War's direction. On the night of November 13, 1942, Fletcher participated in the naval battle of Guadalcanal, a chaotic surface action fought at point-blank range in darkness. The destroyer engaged Japanese warships with guns and torpedoes in a general melee that sank 2 Japanese destroyers and damaged the battleship Hiei. The engagement tested everything about Fletcher's construction. The 5-inch guns fired hundreds of rounds at maximum rate. Torpedo tubes launched spreads at Japanese vessels. The ship maneuvered violently at high speed, placing tremendous stress on the hull structure. The all-welded hull absorbed the punishment without failure. 2 weeks later, on November 30th, Fletcher led a cruiser-destroyer force into the Battle of Tassafaronga. The destroyer made first radar contact with a Japanese reinforcement convoy and engaged in another night surface action. When the cruiser USS Northampton took torpedo hits and began sinking, Fletcher rescued survivors from the water, using innovative techniques to pull men from the sea rapidly. These early actions established the Fletcher-class reputation for toughness and reliability. The ships could take damage and continue fighting. They could operate at high speed for extended periods without mechanical breakdown. The systematic construction approach that had seemed focused purely on production speed had actually created exceptionally robust warships. By 1943, Fletcher-class destroyers were arriving in the Pacific in growing numbers. The ships formed the backbone of destroyer screens, protecting aircraft carrier task forces. They escorted battleships during shore bombardments, they hunted submarines, they rescued downed pilots, they provided anti-aircraft defense during Japanese air attacks. The versatility came from the original design philosophy. The Fletcher class had been conceived as general-purpose destroyers capable of any mission. 5 dual-purpose 5-inch guns could engage surface targets, aircraft, or shore installations. 10 torpedoes provided offensive punch against enemy warships. Depth charges and sonar allowed anti-submarine warfare. Radar and fire control systems enabled night combat. The long range proved particularly valuable in Pacific operations. Fletcher-class destroyers could steam approximately 4,800 nautical miles at 15 knots before refueling. This range allowed them to operate across the vast Pacific distances that characterized the island-hopping campaign. As the war progressed, the Fletcher class adapted to changing tactical requirements. The original anti-aircraft armament proved inadequate against massed Japanese air attacks. Early Fletchers mounted just 4 1.1-inch guns and 6 20mm cannons. This firepower was insufficient against formations of 20 or 30 aircraft attacking simultaneously. Beginning in 1943, Fletchers received upgraded anti-aircraft batteries. Twin 40mm Bofors mounts replaced the obsolete 1.1-inch guns. Additional 20mm Oerlikon cannons were added at every available location. By 1944, a typical Fletcher carried 6 to 10 40mm guns and 7 to 10 20mm cannons in addition to the main battery. The most extensive anti-aircraft modifications came in 1945 in response to kamikaze attacks. Under the April 4, 1945 anti-kamikaze program, approximately 55 Fletcher-class destroyers had their forward torpedo tube mount removed. This freed deck space for an additional quad 40mm mount, bringing total anti-aircraft guns to 14 40mm and 12 20mm weapons. These modifications demonstrated another advantage of systematic construction. Because all Fletcher-class destroyers used standardized designs, upgrades could be implemented across the entire class. Modification procedures developed at one yard could transfer to all others. Ships returning to the United States for overhaul received identical upgrades regardless of which facility performed the work. The production continued at extraordinary pace through 1944. Bath Iron Works maintained its record of a destroyer every 17 days. Federal Shipbuilding sustained high output while simultaneously building destroyer escorts and merchant vessels. By the war's end in August 1945, 175 Fletcher-class destroyers had been commissioned. The number represented approximately 25% of all American destroyers built during World War II. More Fletchers were built than any other destroyer class in history. The production achievement validated everything Federal Shipbuilding had attempted with USS Fletcher's construction in 1941 and 1942. The human cost of proving these production methods deserves acknowledgement. 19 Fletcher-class destroyers were lost during World War II to enemy action. Another 6 were damaged beyond economical repair. The loss rate of 14% reflected the ship's role in the war's most intense combat. 17 of the 25 Fletchers sunk or declared constructive total losses fell between March and July 1945 during the Okinawa campaign. The destroyers served on radar picket duty, positioned far forward of the main fleet to provide early warning of kamikaze attacks. This exposed position made them priority targets. USS De Haven was lost on February 1, 1943. Just 134 days after commissioning. Japanese aircraft caught her off Savo Island and sank her with bombs. USS Strong took a torpedo from the Japanese destroyer Niizuki during the Battle of Kula Gulf on July 5, 1943. The torpedo was fired from 11 miles away, believed to be the longest-range torpedo kill in history. The Battle off Samar on October 25, 1944 saw 2 Fletchers lost in desperate surface action. USS Johnston and USS Hoel engaged Japanese battleships and cruisers to protect escort carriers. Both destroyers fought until sunk by overwhelming gunfire, primarily from the battleship Yamato. The crew's valor earned Presidential Unit citations and medals of honor. These losses, while tragic, occurred in combat operations that demonstrated the ship's capabilities. Fletcher-class destroyers fought in every major Pacific battle from Guadalcanal through Okinawa. They accounted for 29 Japanese submarines sunk. They participated in countless surface actions, shore bombardments, and anti-aircraft engagements. The ships accumulated impressive combat records. USS Fletcher herself earned 15 battle stars. USS Nicholas earned 16 battle stars. USS O'Bannon earned 17. These battle stars represented participation in major engagements, where the ship's contributions proved significant. The production methods that enabled building 175 Fletchers in 3 years carried implications extending far beyond the ships themselves. Federal Shipbuilding and Bath Iron Works had proven that systematic industrial approaches could produce complex weapons systems at unprecedented scale and speed. The key insights centered on prefabrication, standardization, and workforce specialization. Prefabrication allowed parallel production that collapsed construction timelines. Standardization enabled distributed production across multiple facilities. Workforce specialization permitted rapid training that made skilled labor scalable rather than limiting. These insights transferred to other shipbuilding programs. The destroyer escorts built in 1943 and 1944 used identical construction approaches. The Allen M. Sumner-class and Gearing-class destroyers that followed the Fletcher design adopted the same prefabrication and welding techniques. The Liberty ship program run by Henry Kaiser used parallel methods for merchant vessels, though Kaiser came to similar conclusions independently rather than learning from federal shipbuilding. The coincidence demonstrated that systematic industrial thinking applied to shipbuilding inevitably led to certain approaches regardless of who implemented them. Post-war, the legacy extended globally. When Japan and South Korea rebuilt their shipbuilding industries in the 1950s and 1960s, they studied American wartime construction methods. The massive shipyards at Ulsan and Nagasaki that would dominate world shipbuilding for decades drew directly from lessons learned building Fletcher-class destroyers. The ships themselves enjoyed remarkably long service lives. While designed as wartime emergency vessels, Fletchers proved so well built that many served for decades. When World War II ended, most Fletchers were decommissioned and placed in reserve. The outbreak of the Korean War in 1950 brought many back to active duty. During the 1950s, 39 Fletchers underwent extensive modernization under Project SCB-74A. The conversions reduced main gun armament to 4 5-inch weapons and removed a 1 torpedo mount to accommodate anti-submarine weapons. A new ahead-throwing weapon called Weapon Alpha was installed. Some ships received trainable Hedgehog projectors. 18 ships were redesignated as escort destroyers, optimized for anti-submarine warfare. These received additional sonar equipment, improved depth charge systems, and enhanced submarine detection capabilities. All reverted to standard destroyer designation in 1962 as the Navy abandoned the escort destroyer classification. Many Fletchers transferred to Allied navies during the 1950s. Countries receiving Fletchers included Italy, Germany, Japan, Turkey, Greece, Spain, Argentina, Brazil, Chile, Colombia, and Peru. These transfers under the Military Assistance Program helped Allied nations build modern naval forces while reducing American Reserve Fleet maintenance costs. The foreign transfers demonstrated the ship's continued value decades after construction. Nations receiving Fletchers considered them capable modern destroyers worth operating and maintaining. The ships proved adaptable to different mission profiles and armament configurations. The last Fletcher in United States Navy service decommissioned in 1971, but the class continued serving foreign navies much longer. The Mexican Navy operated the former USS John Rogers, renamed Arm Cuitlahuac, until 2001. This represented 59 years of service from commissioning to final retirement. 4 Fletcher-class destroyers survive as museum ships. USS Kidd in Baton Rouge, Louisiana, preserves a late-war configuration with extensive anti-aircraft armament. USS The Sullivans in Buffalo, New York, commemorates 5 brothers lost when their light cruiser sank during the Guadalcanal campaign. USS Cassin Young in Boston displays a Fletcher-class destroyer in her namesake yard city. The former USS Charette serves as HS Velos in Athens, Greece, preserving both American and Greek naval heritage. These preserved ships allow modern visitors to experience what Federal Shipbuilding's revolutionary construction methods created. Walking through USS Kidd's spaces reveals the welded hull construction that seemed so controversial in 1941. The prefabricated sections are visible in how compartments fit together. The systematic layout reflects industrial design thinking applied to warship construction. The engineering spaces particularly demonstrate the prefabrication approach. The boiler rooms and engine rooms were installed as complete units. The machinery foundations, piping systems, electrical distribution, and auxiliary equipment all show planning for assembly rather than custom fitting. Everything was designed to bolt or weld into predetermined positions. The human experience of serving aboard Fletchers deserves consideration beyond technical specifications. Approximately 300 men crewed a Fletcher-class destroyer. They lived and worked in cramped quarters, endured harsh weather, faced enemy attack, and maintained complex systems under challenging conditions. The crews developed intense pride in their ships. Fletcher sailors considered their class superior to earlier destroyers because the ships were faster, more heavily armed, and more comfortable. The flush deck design that gave Fletchers their distinctive profile also provided better seakeeping in rough weather compared to raised forecastle designs. One unique luxury distinguished Fletcher-class destroyers from most warships. Each Fletcher carried an ice cream maker. This amenity, added following prohibition when alcohol was forbidden aboard American warships, provided morale support that proved popular with crews. Off-duty sailors could get ice cream, a small comfort that mattered during long Pacific deployments. The destroyer force that fought World War II's Pacific campaign represented ordinary Americans doing extraordinary work under difficult conditions. The crews came from every state, every background, every demographic. They learned their trades in abbreviated training programs, then went to sea aboard ships built faster than anyone thought possible. The parallel between the ships and their crews deserves emphasis. Just as Federal Shipbuilding proved that systematized production could create complex warships rapidly, the Navy proved that systematized training could create capable crews quickly. Neither the ships nor the sailors were products of long tradition and generational expertise. Both were products of American industrial and organizational capability applied systematically to wartime challenges. The Fletcher-class story ultimately demonstrates how questioning fundamental assumptions about production methods can transform entire industries. In 1941, every naval expert believed destroyers required traditional craft construction. The ships were too complex, the structural requirements too demanding, the quality standards too high for industrial mass production approaches. Federal Shipbuilding's bridge engineers questioned these assumptions, not from maritime expertise, but from manufacturing experience in an entirely different field. They recognized that destroyer construction shared fundamental characteristics with bridge construction. Both involved joining steel sections into complex structures requiring precise alignment and structural integrity. The bridge engineering insight that transformed destroyer production was simple but profound. If you design components for prefabrication and manufacture them to tight tolerances, they can be assembled rapidly without custom fitting. This insight, obvious in retrospect, contradicted generations of shipbuilding tradition. The resistance Federal encountered when proposing all-welded construction and prefabrication reflected genuine concerns grounded in legitimate experience. Welding was relatively new technology in 1941. Welding failures on some Liberty ships would later validate concerns about inadequate welding procedures. The Navy's skepticism was rational, given available information. What made Federal's approach successful was systematic engineering rigor. The company didn't simply adopt welding and prefabrication casually. They developed specific welding procedures, trained welders systematically, implemented quality control throughout fabrication, and tested results extensively. The engineering discipline ensured that innovative approaches didn't compromise structural integrity. This combination of innovative methods and engineering discipline characterized American industrial achievement during World War II. The nation didn't simply outproduce adversaries through brute force scaling of traditional approaches. American industry innovated systematically, applying engineering thinking to manufacturing challenges and implementing solutions at unprecedented scale. The Fletcher-class program exemplified this achievement perfectly. 175 complex warships built in 3 years using methods that didn't exist when the program started. Ships that entered service quickly, fought effectively, survived combat, and served for decades. Production that started from zero in 1941 and peaked at a destroyer every 17 days by 1944. The financial costs were substantial but justified by output. Bath Iron Works invested approximately $20 million, expanding facilities for Fletcher production. Federal Shipbuilding invested similarly in fabrication shops and building ways. The Navy funded much of this expansion through facility contracts that paid for construction before ship production began. Each Fletcher-class destroyer cost approximately $6 million to build at average wartime prices. The 175 ships represented approximately $1 billion in total investment. This compared favorably to the Essex-class aircraft carriers that cost approximately $70 million each, or Iowa-class battleships at $110 million. The return on investment, measured in strategic value, proved exceptional. The Fletcher-class destroyer force enabled American carrier task forces to operate aggressively throughout the Pacific. The destroyers provided anti-submarine protection that allowed the amphibious forces to conduct island-hopping campaigns. They delivered gunfire support for landing operations. They rescued downed pilots, extending air operations. Without the Fletcher-class production surge enabled by Federal Shipbuilding's innovative construction methods, the Pacific War would have progressed differently. The Navy would have lacked sufficient destroyers to screen carriers, hunt submarines, and support amphibious operations simultaneously. The timeline to victory would likely have extended, perhaps significantly. The comparison to adversary production reveals the magnitude of American achievement. Japan built approximately 60 destroyers during World War II, less than half the Fletcher-class total alone. German destroyer production reached approximately 40 ships. Neither nation developed industrial production methods comparable to American approaches. This production disparity reflected fundamental differences in industrial capability and manufacturing philosophy. Japanese and German shipyards continued using traditional craft methods throughout the war. They built excellent individual ships, but couldn't scale production effectively. American yards treated shipbuilding as industrial manufacturing, requiring systematic engineering rather than craft tradition. The philosophical difference mattered more than raw industrial capacity. Even if Japan had possessed equivalent steel production and shipyard facilities, their construction approaches would have prevented matching American destroyer output. The limitation was conceptual, not material. Federal Shipbuilding's achievement, thus, represents victory through innovation in manufacturing process, not merely through resource advantage. The company succeeded because engineers thought systematically about how destroyers could be constructed differently, not just faster. They questioned assumptions, tested alternatives, and implemented solutions that transformed production. The story deserves remembering because it illustrates permanent truths about innovation and manufacturing. Breakthrough performance improvements typically come from fundamental rethinking of processes, not incremental optimization of existing approaches. The gains Federal achieved through welding and pre-fabrication exceeded what any amount of craft refinement could have delivered. The resistance Federal encountered from traditional naval experts illustrates how expertise can paradoxically limit innovation. Naval architects knew destroyers intimately. Their knowledge created conviction about what methods would or wouldn't work. Federal's bridge engineers, lacking that specialized knowledge, weren't constrained by those beliefs. This pattern appears repeatedly in industrial history. Outsiders with relevant but different expertise often drive innovation in established fields, precisely because they aren't bound by industry consensus about what's possible. Federal's bridge engineering background provided the insights that revolutionized destroyer construction. The systematic training approaches Federal developed for rapidly expanding their workforce carried implications beyond wartime production. By proving that complex manufacturing could be performed by workers with narrow specialized training rather than requiring comprehensive craft expertise, Federal validated manufacturing philosophies that would reshape American industry. The post-war shift towards specialized assembly line manufacturing in countless industries drew partly from lessons learned in wartime production. The idea that complex products could be built by workers, trained for specific operations rather than requiring master craftsmen, became foundational to modern manufacturing. The Fletcher-class destroyers themselves stand as monuments to this transformation. Every ship represents the moment when American industry demonstrated that engineering thinking applied systematically to manufacturing challenges could achieve what traditional approaches considered impossible. USS Fletcher, the lead ship of the class, served with distinction through World War II and into the Cold War. The destroyer that launched on May 3, 1942 carried hull number DD-445 and a revolutionary construction approach that would transform naval shipbuilding worldwide. The ship decommissioned on October 1, 1969, sold for scrap on February 22, 1972. 27 years of service from a vessel built in 7 months. The story validates the engineering excellence behind Federal Shipbuilding's revolutionary methods. Today, the Fletcher-class legacy lives in the destroyer construction methods used worldwide. Every modern destroyer built with welded hulls and pre-fabricated sections owes intellectual debt to Federal Shipbuilding's innovations of 1941 and 1942. The Arleigh Burke-class destroyers currently serving in the United States Navy use construction approaches descended directly from those developed for Fletcher-class production. The transformation from craft to industry that Federal Shipbuilding achieved between 1941 and 1945 demonstrates how questioning fundamental assumptions and applying systematic engineering to manufacturing challenges can accomplish seemingly impossible production goals. The 175 Fletcher-class destroyers built during World War II represent not just naval power, but industrial capability, weaponized through innovative manufacturing process. They prove that in modern warfare, how weapons are produced matters as much as how they're designed or employed. The engineers who conceived these construction methods, the workers who implemented them, and the sailors who took these ships to war were all engaged in proving that American industrial and organizational capability, properly mobilized and systematically applied, could overcome any production challenge. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.